So welcome to our seminar series in the Gemini Center on Quantum Computing. Our speaker today is Jakub Mareček, and Jakub received his PhD degree in computer science from the University of Nottingham in 2012. He has been a tenured faculty member at the Czech Technical University in Prague since 2020. Previously, he had also worked in two startups at the University of Edinburgh, University of Toronto, IBM Research Ireland, University of California, and and University of California. His research interests include the design analysis of algorithms for optimization and control problems across a range of application domains. At IBM Research, he co-chaired the Quantum Computing Professional Interest Community. He has co-authored more than 70 journal and 40 conference papers. And he is a co-inventor of 9 families of awarded US patents and several pending patent applications. So if you're ready, Jakub, you can take it from here.
All right, so thanks so much for the invitation. And this talk essentially tries to answer a non-trivial question, and that is whether by using quantum computers in solving an optimization problem, and that could be either exclusively using the quantum computers or using some combination of the classical and quantum computers, we can improve upon what we can do classically. And I think that some of you may know me as an optimization person, certainly Knut Anders and some others would. But more recently, we have been looking into several questions which are on the interface of optimization and quantum computers or quantum information theory. So this started with some adventures in non-convex, non-commutative polynomial optimization, which are sort of omnipresent across quantum optimal control and quantum information theory when you have the right sort of optics. And then we have looked at some applications of commutative polynomial optimization more recently. And this talk relates to 2 papers which concern with algorithms for the near-term intermediate scale quantum devices. And so specifically, it mostly concerns with the results from a paper with Daniel Egger and Stefan Werner at the IBM Research Zurich. And I'm most grateful for that collaboration. So the big picture is that when you read many white papers on quantum computing, combinatorial optimization is mentioned as an application of the near-term intermediate scale quantum devices. And many people see it as like a promising avenue towards quantum advantage, towards being able to solve something which is genuinely useful on the quantum computer or combination of the quantum and classical computer, then we would be able to using the classical computer on its own. And in some ways, I think that this is promising in the sense that we have relatively small instances of optimization problems, which we don't know the exact optimum of. So if we had an approach on the classical computer to solve those, we would have come up with the solutions some time ago, but we don't have that. So sort of they're well-studied problems where classically we have not been able to solve them. And those sort of could correspond to sort of a 500 qubit circuits quantumly in principle. On the other hand, we don't know really whether any NP-hard problems can be solved with polynomial problem in polynomial time quantumly. this is sort of not clear whether that's a sort of a major roadblock, because in the classical case, we also don't know whether NP-hard problems can be solved in P. So maybe this sort of need not be much of a worry. Now, to appreciate what people have been trying to propose in this area, I think that it's good to start with some very early history. And the early history would be the work of Born and Fock in 1928, who have formulated the so-called adiabatic theorem. And this essentially says that if you have some start system, start Hamiltonian, and some target Hamiltonian, some target system, you can track a path from the start system to the target system, such that if you start in the ground state of the start Hamiltonian, you will end up in the ground state of the target Hamiltonian. And this is sort of a conditional because the Hamiltonian has to be gapped and level crossings have to be avoided, and the small enough time step needs to be applied in this path following procedure, where the small enough depends on the gap at any point throughout this path following procedure. Now, this really motivates much of this work, and this is sort of like physics textbooks material since maybe 1930s. So there is no dearth of people who have tried to make it work in physics. And more recently, in the past half century or such, people have been trying to use similar ideas in numerical optimization, and specifically numerical algebraic geometry to quite some extent. And so sort of based on these ideas, you can get classical solvers as well. And for a wide range of problems in numerical algebraic geometry, this is actually some of the most successful solvers, full stop. So these two textbooks are two examples of well-known textbooks which try to use these same ideas classically, and where you would have a substantial amount of analyses of such methods classically. Now, on the quantum side, I think that there are several reasons why you should take interest. So the first one is that you can put together a form of quantum computing known as the adiabatic quantum computation. And this essentially is equivalent in the computational power to the standard model of quantum computing, where you work with quantum circuits. So whatever you can do with quantum circuits, you could do using the adiabatic quantum computation. And so at a very high level, this is sort of a very powerful tool indeed. Now, the paper which is mentioned at the bottom, really an archive preprint since 2014, is an attempt, and a very sort of a high-level attempt at trying to put together a near-term implementable version of this. And in the following, we'll see some sort of limitations thereof. But before we see the limitations, I think that it's important to realize that this is very prominent, and it has some sort of a self-reinforcing aspect to this. So these are some of the best cited papers in quantum computing, and they get prominent attention in some of the best venues in physics, nature physics, science, reviews of modern physics. So people see this, that sort of people publish in good venues with these ideas, and they try to develop them, and then they get published, and then people see that this is well cited, and then that there is this self-reinforcing sort of feedback loop. Now, the main idea behind this quantum approximate optimization algorithm, also known as QAOA, is beguilingly simple. And it essentially tries to, in some ways, abstract away from the path following aspects of the adiabatic computing, and tries to consider a very simple step to be run quantumly, and then a very non-trivial step to be run classically. And so specifically, this is based on the observation that in order to compute certain expectation values, the complexity classically grows exponentially with the dimension of the Hilbert space, whereas quantumly, the complexity grows only polynomially. And so the main idea is, again, like a closed loop, alternating between the quantum computation of certain expectation values, where you essentially look at the evolution of this Hamiltonian HI, and the circuit you run tries to approximate as closely as possible the evolution of the Hamiltonian HI, or rather some parametric version of this quantum circuit seeks to perform the evolution or simulate the evolution of the Hamiltonian HI parametrized by this phi I. And then classically, you try to set the values of the parameter phi or phi I. This is a minor typo. And you would like to set the values so as to minimize the values you would sort of measure the expectations of subsequently. And so sort of you iterate between the classical part, which is an optimization problem, and the quantum part. And here the original Hamiltonian can be, for instance, an Ising Hamiltonian encoding any number of well-known problems starting with MAXCUT. So now the sort of the bad, right? Why this is not necessarily a great idea is that the classical part of the optimization is actually hard. And so you're trying to solve an NP-hard problem to start with. And it turns out that each step of the classical optimizer in the loop of the previous slide is NP-hard as well. Actually, we have some follow-up work to this paper, which shows that it's even worse. But even if you take this at face value, you're essentially saying, I try to solve NP-hard problem by solving repeatedly an NP-hard problem. And it's not completely clear what is the bound on the number of those sort of NP-hard subproblems to solve in order to solve the original NP-hard problem. Right?
Quick question,
Mm-hmm.
because I'm aware of this result, but and I don't quite remember the details, but they have some assumption. And I think one of them is that they don't have a problem Hamiltonian inspired ansatz, right? It's there are some limitations which makes this not generally applicable.
All right. So sort of like I'm not saying that this is like the end of the road, right? That's why I'm not sort of more than like half into the talk, but I'm saying that sort of it is hard, right? And
I agree on that part.
we have some follow-up again, which tries to show the iteration complexity of some popular stochastic approximation methods for the training of the parameters of the parametric circuit. And again, like we may have some luck and not in the worst case, but on average or in expectation, this can be sort of quite successful. So there are some sort of positive sort of results as well, but sort of in theory, this seems a bit of an sort of obstacle to sort of a circumvent. Now,
yes, I think I also remember another paper. Sorry to interrupt.
Yeah, no worries,
trying to make this more interactive. I think I also remember there was a paper that says that there's a certain threshold where if you increase the number of parameters in your QAOA, then before this threshold, every local minima is sort of a bad minimum. But below this, if you go beyond this threshold, you have enough parameters, then you have the same as in classical machine learning.
Yes,
where you basically have every local minimum
yeah.
is a good one.
Yes, this is well known in the sort of optimization for machine learning community, that if the system is very much over parameterized, then you can prove a lot more about the global convergence than if it's not. But the difficulty here is that sort of this over parameterized means you need more qubits, and that may not be readily available yet, right? But
yes,
so sort of I think at the previous slide somehow was the theory, right? And now this slide is really the ugly facts about the practical performance of these algorithms. And so the way to read this is that we have 4 ensembles of Erdős-Rényi graphs. So each of those plots corresponds to one ensemble of random graphs. And here in each of the 4 subfigures, we compare 2 classical approaches, which are very much textbook material, with the present best approach based on QAOA as of last year, which is known as the recursive quantum approximation optimization algorithm, and which is sort of the previous state of the art. And then our variant of this, which is this warm-started recursive QAOA. And this essentially shows that sort of all of the previous work on the QAOA is dominated by polytime classical algorithms, right? So in particular, the black bar here is a polytime classical algorithm, which in some particular fashion rounds an SDP relaxation. So you, in polytime, compute an SDP relaxation of MAXCUT, and then you, in some polytime fashion, round this relaxation. And you can obtain very good solutions indeed. So sort of in these 4 random ensembles of admittedly quite small graphs, you can get the exact optimum in roughly 3/4 in the top left to 40% in the bottom right of the cases. So in these small graphs, the classical approaches running in polytime are actually very successful. So saying in the orange bar that the previous best in terms of QAOA is also quite successful is in some ways no big deal, because the classical approaches are quite successful too, right? So here, the takeaway message from this is that if you start from the equal uniform superposition state in the QAOA, it seems very hard to improve over what you can do in polytime classically. So now the main message of our paper on the warm starting is really that you don't have to start from this usual superposition initial state, but rather you can use whatever you can get classically in polytime and start from there. And then instead of trying to answer the question, can we reach a certain quality of the solutions in expectation or similar, we can ask the question, can we improve over what we can do classically using the quantum computing? And obviously there are many design choices in designing such an algorithm, notably what to round, how to round, and when to round some relaxation. And so here in this talk, we'll explore two of the best known approaches. One which is based on considering the quadratic unconstrained binary optimization, where we have a quadratic form and trying to find a solution over the binary variable in dimension n, and where we relax this to the quadratic programming per se, where we are trying to minimize a quadratic form over a variable which is continuous valued between 0 and 1, again in the n dimensions, or to consider the semi-definite programming where we replace the n dimension vector with an n times n symmetric positive semi-definite matrix. And this is sort of a well-known to produce an excellent guarantee, and in some ways the best possible guarantee in the classical setting. So now, in order to make use of this quadratic programming relaxation for a start, quantumly, we want to come up with two things. So the first one is the encoding of the solution of the quadratic program into the initial state. And it turns out that this is possible. And in particular, when we have a solution which would be C star in this slide, you can look at the block sphere on top, and you can essentially come up with rotation around the y-axis, which produces the effect that with probability C star I, you will be measuring the 1 on this qubit if you take a measurement. So sort of you encode the classically computed solution for the ith coordinate of the QP into the ith qubit using a controlled rotation around the y-axis, right? So that's suggested on the left, and we are sort of, that's our, in some ways, like a start system. Now, we would like to track the evolution of a mixture of a more complicated Hamiltonian, where we would know that essentially one of its eigenstates is the state we start with, and its ground state is the global optimum of the QAOA. And again, this is plausible. This is sort of something we can put together. And in this particular case, the interesting observation is that this can be done very easily with essentially 3 rotations per qubit. And so that's what's sort of displayed at the bottom. Now, there are several technical issues, and the most sort of prominent in some ways is that this approach suits really well the case where you have truly continuous valued results of the relaxation bounded away from 0 and 1. Because if it turns out that the values would be 0 or 1, then you would never be able to flip the value. So in order to avoid this, we use some sort of a regularization term, and that's what's displayed at the bottom left of the slide, where we can tweak the angle in the rotation to make it possible to escape even from the 0 or 1. Now, the alternative is that we can, instead of sort of trying to compensate for the rounded values, we could embrace the rounded values. And in the paper, we describe at considerable length that on the interface of applied probability and optimization, there is something called sticky Brownian motion, which people use to analyze a process where you essentially solve an SDP, round the values which look the closest to 0 or 1, and then solve a smaller SDP. And quantumly, you can do a very similar thing, and that underlies the notion of the recursive QAOA, and our extension thereof, which would be the recursive warm start procedure. So essentially what we do is that we compute the SDP classically. We generate cuts using the Goemans-Williamson randomized hyperplane rounding, again, classically. Then we run the warm start QAOA procedure. We see what values would be most likely to be fixed. And then we actually fix them. And we run a smaller problem on 1 less qubit using the Hamiltonian on the left. So there are many more options, right? So I think that these 2 options really just scratch the surface, because you could round many more things. There are many alternative relaxations you could run. You could round them in a much more sophisticated fashion rather than just the random hyperplane rounding we use here. And this really opens a lot of opportunities in some ways. But I think that even with these 2 systems, the take-home message is that in some of these small random graphs, Erdős-Rényi random graphs, we can improve over what we could do classically in practice. And so I think that that's in some ways encouraging, right? So sort of you take an approach classically, which would be the state of the art, you add the quantum component, and you improve in the empirical results by a small amount. So that's not sort of something to write home about. This is not a theorem that this has to happen or similar, but I think that it's like a positive indication for a change. Now, I know that I'm over time now, but I should like to mention maybe at the very end that a very interesting sort of aspect of this is related to the unique games conjecture. And so sort of a unique games conjecture is a very prominent conjecture in theoretical computer science, which says that a particular problem, which is sometimes known as unique label cover, makes it impossible to distinguish between instances which would have an optimum of a small number or an optimum of a large number. And this sort of unique games conjecture then implies that the SDP relaxation for MAXCUT and the Goemans-Williamson rounding, or alternatively this sticky Brownian motion-based approaches, are the best possible classically. And this opens a lot of questions about what's possible quantumly, because there are several variants of the unique games conjecture in the quantum world. But maybe I will have to sort of refer to the paper for the details. And that's my final slide, really. Thank you.
Thank you very much. It's tough to give a round of applause with muted participants.
No
yeah, the virtual applause, very good. One quick question, which is sort of maybe a very high level question, because on the high level, this warm starting uses a lot of classical knowledge, and this helps to improve the quantum and lifts us sort of above the classical and the quantum, what you can achieve there. Do you, not in the same way, but maybe in a different way, do you expect this could happen also for VQE, for quantum chemistry applications?
Yes, absolutely. So in some sense, whatever you can do for QAOA, you can do for VQE. In some ways, it's almost the same thing.
Okay. Are there any more questions? If not, then thanks very much.
Thank you. And it was a pleasure.
Thank you.